And so the other thing that is you're going to want to just know in general what's going to happen. If we change the concentration of one reactant after it's been at equilibrium, what happens then if we change that concentration, how does it regain equilibrium? Okay, so very general type things. All right, so let's take a look at a very generic reaction where we have A2 plus B2 in equilibrium with 2AB. So we're going to say that the spheres here are representing our atoms and then combining the spheres to make molecules. So the red is A, or A2. B is blue, okay? And so we can take a look at this figure and assume that perhaps that each molecule is representing 1 mole and we've got a liter volume. We can pretend we've got some numbers here that we can play with. So if we count up the number of molecules in this box of AB, we'll find 6. We'll have 1 of A2 and 1 of B2, and we're just going to pretend that these are moles per liter. Okay, that way we can do some math with them. So what's going to happen to this mixture? Okay, we have a little bit of everything. It's possible that we're at equilibrium. Our K value is 1.5. So we need to calculate Q in order to determine which direction we're going to go to reach equilibrium. So our Q is going to be equal to AB squared over A2 times B2. I believe our next, go back. So if we calculate Q for this box, we're going to have 6 squared over 1 times 1, which is 36. So our Q is greater than K. K was 1.5. So in order to regain equilibrium, which direction does the reaction proceed? Towards the reactants or products? Q is greater than K. What's towards reactants? Towards products? Okay, so if Q is greater than K, that means our numerator is greater than our denominator, so we have more products than reactants. So we should go towards products, which means to the right. I really hate the right and left nomenclature. There's a really good chance it'll show up on the exam. I'm trying to get it off. Okay?
So right is products and left is
Yes. Yes. Right again?
Yes, I was able to slide the rest of that. On slide 26, it says if Q is greater
Oh, yeah.
than K, right?
There's more products, right. I just messed it up in my head. There we go. See, the slide has some math. Nope. Okay. Make sure you are familiar with the right and left products, reactants. But like I said, not my preferred method. What's up?
It says left on the slide, but you said right.
Yeah, that's why I was confused.
Did I mess up left and right in there? Okay, we can do the same thing with these different boxes, different ratios of AB and A2 and B2. Again, calculating Q and comparing to K. All right, for our middle box where AB is 3, A2 is 3, and B2 is 2, we're going to end up with Q is equal to 3 squared over 3 times 2. So we'll end up with 1.5. So in this case, Q is equal to K, and we're at equilibrium. All right. So the last box, we only have 2 products, 3 each of the reactants. We'll end up with Q is equal to 0.4, which means that we have more reactants than are expected at equilibrium, so we're going to go towards the product side. Okay? So one of the ways that we can say this is that the reaction is going to shift towards the product side. Okay? Questions on that? Questions? So let's take a look at this example. We've got our Haber reaction. We're forming ammonia from nitrogen and hydrogen. Our K value for this reaction is 6 times 10 to the minus 2. And we're saying that at equilibrium, we have these following concentrations. N2 is 0.399, H2 1.197, and NH3 is 0.202. Now what we're going to do is remove some ammonia, okay, so that we have a new concentration of NH3 of 0.002. And I want to find which direction the reaction must proceed in order to reach equilibrium. So let's actually have you guys do this. What do you expect to happen? We're going to form more reactants or more products? 4 more products. So calculate Q and make sure that's what you get. All right, feel free to work with your neighbor. All right, don't forget about squaring the ammonia concentration, cubing the hydrogen concentration. Those are easy mistakes, easy forgets. That's fair. Anyone get an answer? I ended up with 5.85 times 10 to the minus 6. So what does this tell us? Q is less than K. Which way does the reaction proceed? Towards the products. So there's more reactants than expected at equilibrium. The reaction proceeds towards the products. Okay, so we can show this mathematically. If you forget the general trends that we're going to talk about with the Chatelier principle, you can always make up some numbers and play around and see how what the effect is. We'll just kind of keep looking here at this reaction. So let's say we're at equilibrium. Oh my goodness. We're at equilibrium, and then we're going to increase the ammonia concentration. Okay, the concentration of N2 and H2, we're going to leave the same, but we're going to add more ammonia to the reaction. And in that case, you would calculate that Q is greater than K, and you would expect the reaction to shift towards the reactants. So we're going to form more nitrogen and more hydrogen. Okay. If we increase the nitrogen concentration, okay, recalculate Q, find that Q is less than K, and we're going to shift towards the products. So you only have to increase the concentration of one of the reactants in order to produce a change, or one of the products in order to make a change. Okay. So I'm going to kind of skip ahead here. So here's examples for changing all the various concentrations of each of the reactants and products, and what the effect is. Again, if you remove a reactant, so here N2 is decreased, we're going to actually force the reaction to go back towards the reactants. Okay, so it shifts to the reactants. I think we talked about everything else. Increase hydrogen, shift towards the products. Pretty straightforward with concentration. Okay. Here's a figure to help you kind of think about what's happening. This is looking at our ammonia reaction, formation of ammonia. We've got partial pressure of gas on our y-axis and time on our x-axis. And so we're saying that we have some sort of equilibrium already in place. And then at some point in time, where this dotted line is, we're going to spike the system with some hydrogen. And so you'll see the sharp increase in the hydrogen concentration. And then the reaction will proceed. And we're going to form more products. And when we regain equilibrium, if you compare the concentration or partial pressure of ammonia at the new equilibrium compared to the original equilibrium, you'll see that there's more ammonia present. And there's actually less nitrogen than our initial equilibrium. Why is that? It reacted away, right? You end up with more hydrogen than initially, but that's because we spiked the system with hydrogen. Okay? If you kept spiking with hydrogen, and re-equilibrate, you would end up with higher and higher concentrations of hydrogen, and that nitrogen concentration would be depleted. Make sense? And of course, more and more ammonia. And this is the opposite effect. Okay, so here we have again our initial equilibrium of hydrogen, ammonia, and nitrogen, and somehow we remove some of the ammonia. So you see a sharp decrease in the ammonia concentration, and then we allow equilibrium to be regained. Okay, so what that's going to do is force some of those reactants to react and form more products, and eventually we regain equilibrium. We have a little bit more ammonia produced. And our nitrogen and our hydrogen concentrations are decreased. This is actually one of the ways that refineries or places that make ammonia, industries that make ammonia, will force that reaction to occur more, is that they're constantly removing ammonia from the system. And that ensures that the reaction keeps driving forward. Okay. Questions on changing concentration? All right, so let's look at the effect of changing pressure. We're going to talk about, just in general, for changing pressure on a system. Imagine you have a flask, it's sealed. Okay, you're going to figure out 3 ways that you can change the pressure. One is you can add or remove gaseous product or reactant, okay, or add or remove something reaction that's taking place in this vessel. Somehow you're able to, stick a syringe in the seal and pull out some of the product only, or you're able to add some of the reactant or some of the product, however that may be. That changes the pressure of the system. Okay? Anytime you're removing a gas from the system, you're taking away material and therefore lowering the pressure. The other way that you can change the pressure of a system is to add an inert gas. So this is a gas that's not going to react. It's basically just in there, making the overall pressure increase. It doesn't change the partial pressure of the gases that are involved in the reaction that we're concerned with. And that's gonna be an important fact, okay? The other thing we can do is change the volume of the container. Make the container bigger. What happens to the pressure? Container bigger, pressure goes down. And make the container smaller, pressure goes up. Okay? So here's a figure that's sort of showing that. A little bit blurry, apologize. So we're going to say that we're going to look at our middle box here first. We have a reaction in equilibrium where we have 2A, which are the red spheres, forming B, which is the green sphere. Okay, and this is an equilibrium, yes?
So, like on the exam, will we be asked, like, combining, I guess, the concentration change and the change in pressure, since, like, if you add or remove?
You could do that stepwise.
Okay.
It's possible. I don't know if I have any homework problems that do that, though. Yeah. Okay, so A and B are in equilibrium. And then the first thing we're going to do is we're going to decrease the volume of the box and thereby increase the pressure. And what do you see happens? A lot fewer A spheres and a lot more B spheres. A lot fewer red, a lot more green. All this isn't colorblind friendly, I'm sorry. If you're colorblind, I apologize. Here's red ones. Okay. All right. So then equilibrium is established. This is an equilibrium mixture. And so what's happening is that the moles of the side of the reaction with the fewer moles of gas is favored at higher pressure. So say we can write this out a little bit. Okay. If pressure is increased, the system responds by lowering its pressure by favoring the side of the reaction with the fewest moles of gas. And if you want to shorten that even more, if the pressure is increased, the system responds by favoring the side of the reaction with the fewest moles of gas. Okay. So in this example reaction, we have 2 moles of gas on our reactant side and 1 mole of gas on the product side. All right. So when we decrease the volume of the system, like we do to the left side, tested myself, we end up forming more product. And that's simply because that has the side with the fewest moles of gas. If we increase the volume of the system, we end up favoring the side with more moles of gas. Now the gas is essentially trying to fill the space, okay? And so it produces, it favors the side where there are more particles, okay? So that's what's happening here. So you can see there's a lot more red spheres on this box, the larger box. I'm not going to circle. There's 4 green ones. If you are colorblind, there's 4 green and the rest are red. Questions on that? This pressure one's a little bit funky. So this is also a volume question now. Okay? So we had our system at equilibrium. We increased the volume, essentially lowering the pressure. That's PV equals nRT. Okay? So that's how pressure and the volume are going to be related. And so decreasing the volume, increasing the pressure. Okay? Okay, so here's the summary page. We talked about our 3 ways to change the pressure of the system. The first one was to add or remove gaseous product or reactant. Now, remember, only gaseous product or reactant. Okay, if there's a solid in there and you remove it, it doesn't matter. So that's important. You remove product, more product is formed. You remove reactant, more reactant is formed. Okay? Adding an inert gas. The overall pressure on the system is increased, but because the partial pressure of the reactant or product isn't affected, it doesn't affect the system. It doesn't affect the equilibrium. Okay? So an inert gas does not affect the concentration of our gases in the equilibrium, so equilibrium is not affected. Okay. Changing the volume of the container. Again, this is related to pressure. And when you increase the pressure, the equilibrium shifts to the side with the fewest moles of gas. Okay. Now, that's another one of those problems where you may see the stoichiometry for the equilibrium, but it's only the gaseous stoichiometry that matters. So there could be some solid, but it doesn't affect that rule. Yes?
So adding inert gas doesn't make a shift to the equilibrium.
Right. Adding in inert gas doesn't affect the equilibrium at all. And it has to do with the fact that think about changing the volume one as changing the concentration. We can, let's do that. I'm going to skip ahead a little bit. Here's a real example where we have carbon monoxide and hydrogen gas in equilibrium with methane and water in the vapor phase. So I just wanted to point out here on this slide the moles of reactants and moles of products. So you simply add up the stoichiometry. So there's a total of 4 moles of reactants, total of 2 moles of products. And so if we increase the pressure, we favor the side with the fewer moles of gas, so we form more products. If the pressure decreases, we favor the side with the largest moles of gas, and that's the reactant side. So more reactants are formed to reach equilibrium. Okay, questions on that? All right. Changing temperature. I believe that this wasn't covered on Monday's lecture with Dr. Zelmer. I think he said he stopped here. All right, so this should all be brand new. So we're looking at how changing the temperature affects the equilibrium. In order to do that, we need to know if the equilibrium or if the reaction is exothermic or endothermic. And keep in mind here that that temperature is equal to heat. Okay? If the reaction is exothermic, it gives off heat, that means that we're going to have a negative delta H. Okay, I always do exothermic giving off negative. It's in my head, just do it like that. Endothermic coming in, positive, absorbs heat. Okay? That's a positive delta H. If the reaction is exothermic, we're going to say that heat is a product. And that's an important thing to remember. This is going to be kind of key to solving these types of problems. And if a reaction is endothermic, heat is going to be said to be a reactant. Now, there is one thing that I want to point out, and that is that while we can say that heat is a reactant or a product, the overall temperature of the reaction is the same. It's not like the reactants have a different temperature than the products. Okay? So keep that in mind. There's a sense of reality that this sort of example is not addressing, but it's a useful construct for thinking about the effect of temperature on these reactions. So here's our reaction again with the carbon monoxide and hydrogen gas. Delta H for this reaction is minus 206.2, and for our endothermic reaction, which is our ammonia reaction, a positive delta H of 92. And so on the next slide here, I simply think about adding heat and I just write it out as plus heat on the product side for our exothermic reaction, and plus heat on the reactant side for our endothermic reaction. So now it's really easy to think about the effect of temperature, increasing temperature, on our equilibrium, because we know what happens when we add or subtract product or reactant, changing the concentration. Now this is essentially adding or removing product or reactant, adding heat. Okay, so if we add heat to this first reaction, we're essentially adding a product. So which direction does the equilibrium shift to regain equilibrium? Shifts to the reactant side. And if it's an endothermic reaction and we add heat, this shifts the equilibrium towards the product side. Okay, in order to regain equilibrium, more products are formed in an endothermic reaction when heat is added. So if you have an endothermic reaction and you want to make it form products as much as you possibly can, you heat that sucker up, right? And so like it's just simple like that. The products still have the same temperature overall, but you're essentially adding a reactant to the system. Questions on that? Yeah. Nope. Yep. Okay.
I approve the list. I think that'll last.
Okay. Sounds good.
It's endothermic, it'll always shift with products. Is that always the case, or?
It is always the case that if it's an exothermic reaction, heat is a product, endothermic heat is a reactant. If we said what direction does the reaction shift is if heat is removed, if we cool down the reaction for one of these, then it switches, of course.
Okay.
Yeah, so don't kind of hold that in your head as the thing that needs to change. Just think of it as a reactant or product, and think about adding heat, increasing temperature, decreasing temperature as affecting that concentration. What else do I have? Okay, this was a senior moment. I have no idea. Sorry.
So will that always be the case? Like, if heat is exothermic, it'll always shift towards the reactant.
All right. So remember reaction progress diagrams from last chapter? I'm going to go back to these just for a little bit. So, let me get my cheat sheet here. So, in our box here, I'm basically just wanting you to recall that reaction rate, lowercase k, is dependent on activation energy. Okay, and we saw some of the effects of increasing the temperature on the reaction rate for a reaction, right? And how that's related to the activation energy. Here's a reaction coordinate diagram for a reaction that has a delta H of 0. It's not endothermic, it's not exothermic. Right? What happens if we increase the temperature of this reaction? Does it shift the equilibrium? Not quite. So if delta H is 0, heat is not either a reactant or a product. It basically doesn't have an effect. Okay? So the next slide says no. This does not shift our equilibrium. And here's why. Let's say that we increase the temperature. I'll use a different color. I'll use red. We've increased our temperature. And now we're at this level of energy for our reaction coordinate diagram. EA is now smaller, right? So we've increased the probability of going over the hill. What happens to the forward rate? Does it increase or decrease? Or nothing? Increase, yep. What happens to the reverse rate? The reaction in the first reverse reaction, it also increases. Now, one of the things, remember from the very, maybe you don't, that's fine. From the very first lecture on equilibrium, we said that K forward over K reverse is equal to our equilibrium constant K. So in the case where the activation energy for the reactants, for the forward reaction and the reverse reaction is the same, increasing the temperature has no effect because the rates are affected by the same amount. The rate of the forward reaction and the rate of the reverse reaction are affected by the same amount. So if those are increased by the same amount, K is not affected overall. Big K is no longer affected. Does that make sense? Maybe if we look at a case where there, slide 51 kind of just summarizes what I said. Okay, so let's look at the case where we have an endothermic reaction, positive delta H. Okay, and now we, since we have a positive delta H, heat is a reactant, so I'm just going to go ahead and add it. I got to go back to my blue here. Okay. We know that this is going to shift our equilibrium if we increase the temperature in some direction. Which way will it go? Towards the reactants or products? Goes towards the product side. Equilibrium shifts towards the product side. Okay. What happens to the forward rate when we increase the temperature? Same thing as last time, right? It's going to increase. And the reverse rate's going to increase. But the really cool part comes in when you look at the percent of change, or percent of increase in the reaction rates. I don't know if we explicitly did one of these problems in class during the rate chapter, but you can calculate the percent increase by increasing the amount of temperature based on the Arrhenius equation. Okay? So when we increase the temperature from 270 to 310 Kelvin, the forward rate increases by 1,700%. Okay? The reverse rate doesn't increase as much. It only increases 1,200%. And that's because of the different activation energies that are present. Okay? That magnitude of activation energy shows up in this equation, and it affects the percent increase in rate. And so because these increases aren't the same, what we see is that there we go. That our K value, large K, is increased. Okay. By the way, that Kf over Kr is equal to K. Does that make sense? Yes.
Do we have to know how to calculate the percentage?
No, you're good. You don't need to know that now. That's a different chapter. Yeah.
Will that graph look the same if the temperature is decreased?
Will the graph look the same if the temperature is decreased? What you'll see is the magnitude of EA get bigger on both ends, but
Could you draw for the increase?
okay. Yeah, so if we decrease, use green, I'm thinking it's going to be like this. Same here, something like that.
That's for decrease or increase in temperature?
Oh, wait. That's for decrease. So maybe that's not the most effective way to think about it. Yeah, that's going to be right. So essentially, if you're starting at a certain temperature, and this is where your potential energy is for reactants and products, it's essentially lowering if you lower the temperature.
Okay.
Yeah.
But it's gonna go to the same peak.
Yes. Yes. There was another question, I think. Okay.
So like if you're like raising the temperature, if you were to draw all of the same graph,
Mhm.
the reactants and products shift up, like they shift down even lower.
It'll be like that. Yep. So red is raised T, green is lower. Again, red and green. Sorry, guys. Any other questions? These are good questions. All right. Want to do one example problem? This is this goes back. This is one of the. I picked out one of your homework problems that seemed to give the most trouble, and adapted it. So let's go over this. One more ice problem. I'm going to have you guys work on it. So we have our generic reaction, AD decomposing into A plus D. We've got a 1 liter flask that contains 1 atmosphere of AD initially. After equilibrium is achieved, 0.13 atmospheres of AD remains. What is our KB value? So work on this, work with your neighbor. I'll come around, and then we'll finish this off. Last of the chapter. For A and D. But we're told that after equilibrium has been achieved, there's 0.13 atmospheres of AD left. And so we know that that is equal to 1 minus x. So we can solve for x. We'll get x is equal to 0.87. And then we can plug into to Kp. We're going to have concentration of A times concentration of D. Both of those are 0.87 because they're both equal to x. So 0.87 times 0.87. I'll leave those separate just to denote the fact that they're two different things. And then divided by 0.13. And we'll end up with 5.8. Questions on this? How are you guys feeling about equilibrium? Because you were working with partial pressures in KP. You guys feeling good about equilibrium? Again, this is more tricky stuff with acids and bases starting on Monday. Have a great weekend. No. So here's some more slides, very similar to what we were just looking at. Now, we've got a container with a 1 liter volume. We have NO2 at 1 atmosphere and N2O4 at 0.08 atmospheres. N2O4 is our reactant, NO2 is our product. And now we're going to be using PV equals nRT in this example. So let's see. I stole these slides from Dr. Clark. Well, I didn't steal them, but he let me borrow them. I loved the foot. I just couldn't. This is hilarious to me. That's definitely a Dr. Clarkism right there. So what this is showing you is that by decreasing the volume by half, okay, we can actually predict the pressures for NO2 and N2O4 using our PV equals nRT. So if I skip ahead there one more slide, if you half the volume, the NO2 pressure doubles. Same with the N2O4 pressure. Okay. Adding an inert gas doesn't affect those pressures, so it doesn't really affect the overall equilibrium. It's kind of a funky thing to think about though, because
Increase the pressure of the overall system.
just the overall system. Yep. This slide goes on, but it basically is just showing you that the pressure increasing the pressure favors the side with the fewer moles of gas. So I'm going to leave the rest of the slides, but go back to where we left off. Any other questions?